All right, so today we are going to get to talk about gas stoichiometry, which we're already pros at stoichiometry, right? Stoichiometry is, can you give me kind of the rundown definition of what does stoichiometry mean? What's that vocabulary word mean? Right, we did a whole chapter over stoichiometry before break, but what does that word really mean, or what does that phrase really mean? Or even in even broader terms, tell me, what did we do in the stoichiometry chapter?
We put some quantities on reactions.
That's exactly right. That's what stoichiometry is. It's quantifying chemical reactions, putting numbers to our experiments, putting numbers with our reactions, right? And making predictions about our products. That's really what stoichiometry is, quantifying chemical reactions. And so we're going to do the same thing now, except we're going to be able to dive into the gas realm of it, okay? And in order to do that, we gave ourselves one really clear conversion factor last time called Avogadro's principle. Does anyone remember what that conversion factor was? 1 mole is equal to how many liters? Do you remember that? 22.4. Good. 1 mole is equal to 22.4 liters. But is that true all the time or only some of the time? Only some of the time. And what is the specific time and when that's true?
At STP.
It has to be at STP. Right? That conversion factor is only true at STP. It doesn't work outside of that. It's only true at STP. Now, does this conversion factor depend on what compound we're working with? Or is it true for all compounds? I'm going to need some of you other people to give me some feedback here, right? Because I'm only really seeing 2 of you, maybe 3 of you engaged. So let's get involved here, okay? So does this conversion factor depend on the compound? It does not. It does not. Just like moles don't depend on the compound. There are 6.022 times 10 to the 23rd atoms in a mole, regardless of the compound. The same thing is true about this one, right? 22.4 liters is equal to 1 mole regardless of the compound. So let's go ahead and try a conversion here. This says how many grams of aluminum oxide are formed from 15 liters of O2 at STP. This is supposed to be an arrow. It just didn't copy very well on my slide. Okay, this equation looks like, is it already balanced? It's already balanced. Okay. So we're going to go ahead and start looking at our problem just like we did with chapter 3 in our stoichiometry problems. We're going to write down what we know, 15 liters, and I want to know how many grams of aluminum oxide can be formed. So I'm going to start my T-chart just like I always do with what I know. 15 liters of O2. Let's start working our way through here. If my goal is to get from oxygen gas to aluminum oxide, what do I have to go to? Moles. Moles has to be my middleman, right? Moles is my middleman. So I'm going to convert from liters of O2 to moles of O2. And what's my conversion factor there? 1 mole is equal to 22.4 liters. I'm going to keep going. Moles of O2 to moles of aluminum oxide, right? And what did we call this step of our conversion? It was called the mole ratio step. And this is where we start talking about how many moles of each of these are needed. So this number right here comes from our balanced reaction. And it says 3 moles of O2 are needed to produce 2 moles of aluminum oxide. That's the only part of our chart where moles does not get a 1, right? Is in the mole ratio step. Do we remember that? Okay. If I stopped my calculation right here, what would my final units be? If I stop my calculation, Riley, what would my units be? Moles of Right, it has to be that one because so far, liters of O2 is canceled, moles of O2 is canceled, and I'm left right now with moles of aluminum oxide. But that's not my goal. My goal is grams. So I'm going to keep moving. Moles of aluminum oxide to grams of aluminum oxide, Al2O3. So I need the molar mass to go up here with grams. So let's calculate molar mass of aluminum oxide real quick. What do we think?
102.
I didn't have it quite that high. Maybe I did something. I had it at 74.
I had 102.
Oh, Al2O3. Aluminum is 13. Oh,
27.
you're right. Thank you. 27 times 2. Thank you. All right, 102. There we go. All right. So now we're going to do our math because if I've looked at my units, all my units have canceled. So 15 times 2 times 102 divided by 22.4 divided by 3 gives me about 45.5 grams of aluminum oxide. Okay, so we're going to convert this compound right here into moles of Cl2. So I'll keep marching here. Moles of C2H2Cl4 to moles of Cl2. Now, can I continue my chart and just go moles of Cl2 to liters? No, we already said we can't do that because we don't have conditions at STP. We don't have conditions of STP. So I'm going to find out how many moles of chlorine are present, and then I can work with the ideal gas law from there. This is our mole ratio step. And so these numbers come directly from our balanced equation. So there's no coefficient listed right here, is there? So we're just going to put a 1, and the Cl2 is going to get a 2. Because that's the coefficient listed directly in front of it in our problem. So 75 times 2 divided by 168 divided by 1 gives me 0.893 moles of Cl2. And now I look at my ideal gas law and say I've got pressure, I've got temperature, I've got moles, and our goal is to find volume. How many liters, right? So P times V equals N R T.